Hey there, Algebra 2 students. Welcome back to Miss McGuire's classroom. I'm excited to do our lesson today. We're going to jump right into Unit 4, Lesson 2. We're going to talk about complex roots and complex numbers. We're getting in some true Algebra 2 material today, which is really cool. Don't forget to put your name, period, and the date in the upper right-hand corner. I need your first and your last name. Remember, part of your grade for your weekly notes is having your first and last name on the notes that you turn in, which should be your own. So let's jump right into our lesson. For our objective today, this is what we're going to be learning. I will simplify complex roots by using imaginary numbers, as well as simplify expressions with complex numbers. And you're going to know that you mastered this objective by scoring at least an 80% on the extra practice, which you're going to do after the lesson and then submit to Schoology like we did in our previous semester. So if you recall, when we were solving radicals last semester, we could get this, these graphs are like missing all the arrows, huh? That just really bugs me. And they're missing labels on the X and Y axis. Man, these graphs would get a 0 if I had to grade them, huh? Yeah, let's get those arrows so we know that these things extend forever and ever. All right, so remember when we have a quadratic function, so we're talking about a quadratic polynomial or what we learned the other day is this is a degree 2 polynomial function. So a quadratic polynomial function is a degree 2 polynomial function. Remember, the functions look like f of x equals ax squared plus bx plus c. And when we graph them or when we solve these types of functions, we're always looking for our zeros or our roots or our x-intercepts, right? And when we solve a quadratic function, there are 3 options for the numbers and types of solutions that we can get. We can solve and get 2 solutions or 2 real solutions. And by solutions, I mean x-intercepts. We can solve and only get 1 x-intercept because it only hits the x-axis 1 time. So maybe we get 1 real solution. Or we can have a function that doesn't even hit the x-axis on the real number plane. So notice that I didn't say that this will never hit the x-axis. I said that it doesn't hit the x-axis on the real number plane. So this parabola actually has 2 x-intercepts, but they're not on the real number plane, so we can't see them on this coordinate plane because this coordinate plane uses the real numbers on the x and the y axis. However, if we were to graph this and add in the imaginary number plane, we would be able to see the x-intercepts because it has 2 imaginary zeros or 2 imaginary solutions. And remember, when I'm talking about solutions, I really mean those zeros. What else did we call them? We called them roots and we call them x-intercepts. AKA means, you know, also known as, I almost didn't remember what it stands for. Also known as zeros, also known as roots, also known as x-intercepts. All right. So we can have 2 real solutions, 1 real solution, or 2 imaginary solutions. Now, when we say imaginary, that's kind of a misnomer. Imaginary numbers do exist, but they exist on a different plane than what we call the real numbers. So they've just been referred to as imaginary numbers for a minute. But today, you're going to learn how to actually solve for those imaginary roots. In the past, we would just stop and say, hey, we've got a negative under the radical. We're going to have imaginary roots. We can't go any further. After today, you're going to be able to find the imaginary roots and tell me what they are. So the imaginary number that we use is the imaginary number I. And I is really important because I squared is equal to -1. This is the number one fun fact of your life that you need to have memorized for the rest of your mathematical career. However far you're going to go in math, you need to have memorized that I squared is equal to -1. If you want, you could say it with me. I squared equals -1. This fun fact is going to help us simplify radicals. As you can see in example 1, we need to simplify a radical with a negative under it. And normally that would like break our understanding of math. But today we're going to learn how to expand that understanding and be able to simplify all of these radicals that have negatives underneath them. So it's pretty cool. Let me show you why. Okay, so if I squared is equal to -1, what if I wanted to solve for I? Like if I had x squared equals a number, what would I do to solve for x? Well, what cancels a square? Doesn't a square root cancel a square? So what if I take the square root of both sides? Well, the square root of I squared is just I times I. And when I have a group of 2 under the radical, I can bring one out to represent that pair. Then nothing would be left under the radical. So I just have I is equal to the square root of -1. So what happens is if I squared is equal to -1, that means that I is equal to the square root of -1. So the -1 actually has a square root. It's equal to the number I, the imaginary number I. And today we're going to learn how to use that to simplify radicals with a negative underneath. So we need it in order to take the square root of negative numbers. And I realize I wrote kind of small, zoom in. So the imaginary number I, we need it so we can take the square root of negative numbers. All right, so let's use this knowledge that I just talked about and apply it to some things. So anytime you have a negative under the radical, you're going to want to use I squared. So think about this. If I squared is equal to -1, that means that I can replace the square root of -1. That means I can replace -1 with I squared. Well, isn't I squared really just I times I? Hey, I've got a group of 2 under my radical. I can bring out the number that represents that group of 2, and I have I. And then there's nothing left under the radical, so we don't need it anymore. So I'm left with I. And I like to put a little tail on my I so I can tell that it's an I. We don't want to mistake it for a 1, right? So I put a little tail to make sure you know that it's an I. And I would appreciate it if you would write your I's like that as well. All right. So let's do this together. Actually, I'm going to get you started in part B, and then I'm going to see if you guys can finish it on your own. So taking the square root of -49. If I asked you for the square root of +49, I'm sure you would just tell me it's 7, right? But this time we're taking the square root of -49. So what's that going to be? Well, here's what I recommend. Remember, anytime you have a negative under the radical, I want you to use I squared equals -1. And the way I do that is, think about -49. Isn't -49 the same thing as -1 times +49? Yeah. And then check it out. I've got a -1 here. What can I replace -1 with? I squared. So then I can rewrite this as I squared times 49. Now you simplify this radical from there. Go ahead and press pause and then press play when you're ready to check your work. So as you can see, I broke down I squared as I times I, and 49 is 7 times 7. Well then, hey, I've got a group of 2 I's, a group of 2 7s. So I brought the 7 out and I brought the I out. in front of the radical, there's nothing left under the radical. So it drops out. So the square root of -49 is 7i. Now notice I wrote 7i. I didn't write I7. You treat, even though I is technically a number, so it's not a variable, you treat I like you would a variable. So for example, if you had like 7x, you wouldn't write 7x as x7, right? You would write it as 7x. That's how you treat I. You always list it second and then put like the integer or whatever else first. So we say 7i. Okay. So you treat it like you would a variable, but it's not a variable, it's a number. All right, let's do the square root of -75. So remember, we want to use our knowledge of I squared equals -1 to help us simplify this. Well, -75 could be rewritten as -1 times 75. I can replace -1 with I squared. I can rewrite 75 as 25 times 3. I can rewrite I squared as I times I. 25 is 5 times 5 times 3. So then I've got a group of 2 i's. I've got a group of 2 5's. I'm going to bring one of those i's out in front. I'm going to bring one of those 5's out in front of the radical. And then this time the radical stays in the problem because I've got a 3 left under the radical. So I want to keep it there. So now my final answer is 5i root 3, or 5i times the square root of 3. 5i root 3, you can also say it as 5i times the square root of 3. You might want to practice saying that out loud as well. So 5i root 3. And that would be our final answer. And as you can see from the 3 problems we've done so far, we took the square root of a negative, but our answer is positive. We took the square root of a negative, got a positive 7i. We took the square root of a negative, and we got a positive. Just kidding. We took the square root of a negative, and we got a positive. So when you take the square root of a negative, you don't get a negative number. You get a positive number. You take the square root of a negative, you don't get a negative number, you get a positive number. Just like when we take the square root of a positive number, we always got a positive number. All right, let's keep going. So now the square root of -27. So why don't you try simplifying this from start to finish all by yourself? Remember, you want to use your knowledge that I squared is equal to -1. Go ahead and give this a shot on your own. Press pause and then press play when you're ready to check your work. All right, so hopefully your work looks similar to mine. For the square root of -27, I rewrote it as the square root of -1 times 27. Then, because I have a -1, I know that -1 is equal to I squared. So I replace my -1 with I squared. How convenient. Then I rewrote 27 as 9 times 3. So then I broke I squared down to I times I, and 9 to 3 times 3. And then I solved that other times 3. I've got 2 groups of 2 groups of 2. What am I saying? So I brought out an I out in front of my radical. Did not mean to erase that. And I brought out a 3 out in front of my radical. And then there was still a 3 under the square root. So my final answer is 3i root 3, or 3i times the square root of 3. All right, I hope you all did a good job with that. Now let's talk a little bit about complex numbers. All right, so a complex number is a complicated number. It's still a single number, but it has 2 parts. Kind of like, okay, like an example of a complex number is also like 1 plus the square root of 2. 1 plus the square root of 2 can be written as like a single number. It still represents a number. We could take the square root of 2 and add 1. Like if I got my calculator out here, if I took, let's see, second, the square root of 2, and I added 1, it's 2.4142135624, etc. So 1 plus root 2 is itself a number, but it can be written as an integer plus a radical. So that's a complex number. It has an integer, and then it also has a root that it's either being like added or subtracted to. Well, I can be a part of a complex number. In fact, I is a complex number, actually. I'm going to show you why after I figure out how to close my calculator. So when we talk about complex numbers involving I, or I as a complex number, we write it as A plus BI, where A and B are a rational number or an integer. So A plus BI. So we could also have like A minus BI, A could be negative, all that good stuff. But if A is 0, so if A was 0, we would have 0 plus BI. Well, what's 0 plus BI? Just BI. So if a number only involves I and it doesn't involve the A plus or whatever out in front, then we call that a pure imaginary number. So A plus BI is a complex number. So for example, you could have 7 plus 2i. This is a number. Even though it's written as two numbers, like two parts added together, it still represents a single number. That's why it's called a complex number. Or maybe you have 7 minus 2i. You could have negative 3 plus 2i. But what if you have like 0 plus I, where A is 0 and B is 1? So 0 plus I. Well, what's 0 plus I? I. So I is still technically in the form of A plus BI. A is just 0 and B would be 1. A plus 1 times I is just I. So I itself would be a pure imaginary number. All right, so we can take imaginary numbers and we can add them to other imaginary numbers. We can subtract. Did I just say imaginary numbers? We can take complex numbers and add them to other complex numbers. We can also take them and subtract them from each other. We can multiply them. We can divide them. So today we're going to practice adding and subtracting them, and then we're going to practice multiplying them. So 4 minus 3i is a complex number. Negative 4 plus 3i is also a complex number. And we're going to take them and add them together. Well, technically, like there's a 1 out in front of these parentheses. If I multiply that 1 by the 4 and the negative 3i, is any part of that going to change? No. So I can just rewrite that without parentheses. Then, if we add negative 4 plus 3i, I'm distributing a positive to the negative 4 and the 3i. So a positive 1 technically times negative 4 is just negative 4. A positive 1 times 3i is positive 3i. So just like we would if this was an expression that involved variables, we combine our like terms. Or in this case, because it's a complex number, we combine the like parts. Remember, we treat I like a variable, even though it's not. So we combine our like parts. So 4 and negative 4 are both the integer pieces. So we're going to combine those. And then negative 3i and positive 3i are going to get combined. So what is 4 minus 4? Well, that's just 0. Negative 3i plus 3i is also 0. So this actually just simplifies to 0. That was too easy. Now let's do this one on our own. So 7 minus 2i plus negative 3 plus I. Go ahead and add those together. Remember to combine the like parts. Treat I like a variable, even though it's not. And then press pause and then press play when you're ready to check your work. Give it a shot. So because it's addition, I realized nothing was going to change. So I just rewrote the problem without parentheses. I have 7 minus 2i minus 3 plus I. I combine my like parts. So 7 minus 3 is 4. Negative 2i plus I is negative 1i, or just negative I. And then whenever you write a complex number, you always put the integer piece first, followed by the imaginary part, the part that makes it a complex number. So now let's subtract. So when we subtract, we got to watch out, because we have to distribute a negative to the second set of the parentheses. So the first set still has this positive 1. If I distribute this positive 1 to 5 and negative 3i, they're not going to change. But if I distribute a negative 1 to negative 2, I get positive 2. When I distribute the negative 1 to a positive 4i, I get negative 4i. So let's combine our like parts. So 5 plus 2 is 7. Negative 3i minus 4i is negative 7i. So our complex number is 7 minus 7i. All right, why don't you go ahead and try part D by yourself. Take 8 plus 6i minus 8 minus 6i. Press pause and then press play when you're ready to check your work. So I distributed that negative. So I ended up with 8 plus 6i minus 8 plus 6i. I combined my like parts. 8 minus 8 is 0. So that part dropped out. 6i plus 6i is 12i. And I actually ended up with a pure imaginary number. Now let's do the fun part. Let's do some multiplication. So for example 3, our directions are to multiply the complex numbers and then write our answer in simplest form. And that just means to write your final answer in a plus bi form. So part A, 3i times negative 5 plus 2i. Now, if this was just, let's say 3 times negative 5 plus 2i, what would we do? Well, we would know to multiply this by each part. So we're going to do the same thing, except this time 3 has an I attached to it. So we're going to take 3i and distribute it to the negative 5 and the 2i. So 3i times negative 5 is negative 15i. 3i times 2i is then 3 times 3 is 6, and I times I is I squared. But we have to write this in simplest form. So something a little tricky, well, not necessarily tricky, but something we have to look out for is I squared. What did we learn earlier in this lesson that I squared is equal to? Isn't I squared equal to negative 1? So that means I can replace I squared in this complex number. You're never going to turn something in or like have a final answer that has I squared in it. You're always going to simplify it, because that I squared can be replaced with negative 1. So 6i squared is the same thing as like 6 times I squared. So we rewrite it as 6 times negative 1. Well, then we're going to have negative 15i, and 6 times negative 1 is negative 6. But when I write a complex number, I always want it to look like a plus bi. I'm going to put that integer, the negative 6 first, and the negative 15i second. And notice that the signs followed with, like the negative 15i followed the 15i, the negative 6 followed the 6. So that's our final answer, negative 6 minus 15i. Now you give it a shot. So negative 4i times 3 minus 7i. Go ahead and press pause and then press play when you're ready to check your work. All right, so negative 4i times 3 is negative 12i. Then negative 4i times negative 7i. Negative 4 times negative 7 is positive 28. I times I is I squared. Now what can I replace I squared with? I squared is equal to negative 1. So I'm going to replace I squared with negative 1. So this is really 28 times negative 1, which is negative 28. I want to make sure I write that integer piece first, followed by the I. So negative 28 minus 12i should be your final answer. All right, let's do part C. So part C, 4 plus 3i times negative 1 minus 2i. Now, you might be like, oh no, this looks scary, but stay calm. It's going to be okay. What would you do if this said 4 plus 3x times -1 minus 2x? Wouldn't you just start distributing the 4 to both of those parts and the 3x as well? That's exactly what we're going to do here. We're going to distribute, multiply, simplify. It's going to be okay. So we're going to take 4 times -1, 4 times -2i, 3i times -1, and 3i times -2i. So 4 times -1 is -4. 4 times 2i is -8i. 3i times -1, -3i. And then 3i times -2i, -6i squared. So when I simplify this, not only do I want to combine all the like pieces, but I also want to make sure I do not have I squared left in my final answer, because I squared is equal to -1. And we always want to use that when we can, which is always. So we're going to have -4, -8i, and -3i simplified to -11i. -6 times I squared is -6 times 1. Just kidding. -6 times -1. Excuse me, Miss McGuire. -4 minus 11i. -6 times -1 is +6. Then we're going to take -4 plus 6, which is 2 minus 11i. Notice how I made sure that the 2 is written before the part with the I. So 2 minus 11i is our final answer. All right, you ready to try this on your own? Part D, go ahead and multiply 1 minus 2i times 3 minus 4i. Press pause and then press play when you're ready to check your work. You got this. All right, so I multiplied everything out. I took 1 times 3, which is 3. I took 1 times -4i, -4i, -2i times 3 is -6i, -2i times 4 is +8i squared. Then I realized I needed to replace I squared with -1. I could combine the -4i and the -6i to be -10i. 8 times -1 is -8. So then 3 minus 8 is -5, and then -10i. So hopefully our answers match. Good work. All right, so today there is actually an extra practice. So head on over to Schoology and complete the extra practice problems. Submit them to the assignment when you're done, and then hit that ask for help button when you're ready for me to jump into your breakout room and go over your work on the extra practice with you. All right, I'll see you back in class. Have a great day.